Jnanam Paramam Dheyam. Knowledge is supreme.
Welcome to MOOC course on applications of interactomics using genomics and proteomics technologies. As I mentioned briefly in the last lecture, if you are doing the high throughput experiments, what becomes really crucial that what are the quality control checks you have done. While it is very easy to generate big data now with the advent of latest technologies, especially in the field of proteomics and genomics. But what becomes very crucial now, how close attention you are paying in terms of your reagents available, they are good quality reagents, your assay performance, the quality control checks for that, and then your various control spots or control features which should guide you whether experiment works or it has lot of non-specific values. In this light, microarray experiment becomes very crucial when you have thousands of spots printed on a given chip and you have to now perform your clinical sample applications or various type of protein which you want to test out on the chip. You need to ensure that you have the good guiding controls for the entire experiments. You have good positive controls and negative controls printed on the chip. But then what also becomes very crucial, if you are printing thousands of features on the arrays, how reproducible your printing is, how close your spot morphologies are from one to other. Have you paid enough attention to ensure that there is no batch to batch variation between the slides? Because if for the biomarker discovery program, if you are using large number of patient samples, let us say 100 samples you want to use for a biomarker discovery program. So, you need 100 slides, one for each patient. If there is a variability from slide to slide and batch to batch, you already have so much variability from the individuals, that is the biological variability which we cannot avoid. Each one of us are very unique, very different, and the patient sample will have many things which will be not so reproducible across hundreds of samples. If your features itself are printed on the chip are also non-reproducible, then you cannot make sense of the data. Therefore, making a good chip with the proper quality control checks becomes very crucial. So, in continuation to the last lecture, Dr. Saloni Sonawala, the application scientist from ArrayJet technology, will demonstrate you how to perform reproducible and high quality printing for microarray based experiments. You will also learn about IRIS, which is a camera, and advanced technology that is used for this type of printing of microarray slides. So, let us have Dr. Sonawala to give her talk.
So, I will go back and I am going to open the command center for you. That is your command center. That's the software where the magic happens. This is where all the development of arrays like HuPro and other industrially supported arrays have happened. So, all these people use the command center. The command center is something that you can use. It is like your paint software. You can design which area you want, what arrays, what plates you want. You can pick and choose how many samples you want. You can customize the whole experiment sitting on a computer and designing it from these particular features that I will take you through. Obviously, this is the first tab that gets open. You've got an option. So, what should we do? Let's do one example of something that you want to develop. Just anybody has any idea what kind of array you want or what design you're looking for. I'll leave it to you. Just give me an example. Maybe you have 34 antibodies, you have 12 antibodies. Just give me a number. Anyone? Any number? 22. Okay. So, that's a good number because it can do 12 times 12. So, what will happen is your 2 of will be blocked. So we can design a 22 sample run very easily, and I'll show you how. So obviously most of us use 384 well sample plate. I'm going to reduce this to 1. This is your 384 samples. Now you said 22. Now look what happens when I type 22. The most minimum sample that you can print or you can have is 12, because I showed you the jet spider. The lowest ability is 12. The highest ability is 32. So now it's a good one that you've given me 22, because we are working around it. So 12. If I want to increase this number, it's 24, 36, 48. These are your samples. This is where your sample goes in the plate. And that's how you can fill the plate. And it tells you exactly where you want to put your sample. So everything is automated. You design your run and the software will tell you how to prepare your sample plate. So it will give you a printout that, okay, if you want to print 22 samples, I'll show you where your 22 samples will go so that your experiment will look like how you want it to look. So the software will tell you exactly how to design all that. So I'm just extending this, but I don't want that many. I only want 22. But I can't get 22, I can get 24. So I'll leave it here and I'll go to the next tab. These are the nozzles of the print head. This is sample 1 is distributed across 4 nozzles. Like that, there are 12 samples. Now, again, I want you to tell me how I can get 22 samples instead of 24. And I'll tell you this, I'm able to block some of these dots. I'm able to block them. So I don't use them at all. So, any idea? What I will do is, I'm going to use 11 out of these 12 from the jet spider. I'm going to block this one. Why? Because it's 22. So what I want to do is, I can do 7. If I want to only have 7, I'll block these. So basically, the jet spider will go inside your printhead, but those that I've blocked will not use your sample. You can put a blank or a buffer or something there. So I will only use 7, and they get printed across 7. So let me try and block them, and let me show you what happens. That's your blocked. So now I've got 11. If I move back, I'll have a set of 22 because it's block 2. Do you see that? So now I can print 22 samples because I was able to flexibly just go here, block 1, go back, 22 samples. I could block, if I wanted to just do 7, I had only 6 samples. I'll block all these. And now I've got only 6 samples that I'm working with. So now you've got 12 because you're times 2. So it's 12. So this is where you can modify how much sample you're printing and what you want the jet spider to pick up. So it's not that it'll go inside the plate and pick up all your sample and bring it back. It'll go inside the plate and only 1.3 microliter will be picked up each time. And that is more than enough for your entire assay.
Is there a reason why the samples that are filled are not in one row or all of them like randomized?
That's a very good question. There are 2 options you can do. The filling of the samples in the plate can happen vertically. So it goes, a set of 12 goes first corner of the plate, picks up the 12, then it goes down and it picks up. But you also can do horizontally. Now, I've moved this to horizontal. Let me go back. So these are 12 minus, so there are 6. So what happens, it has to fill up. Because the jet spider is 12, it goes alternatively, so alternate well. So it needs to complete that first top corner before it moves to the next section. Now look what happens. I am increasing the samples.
So why does it seem to go?
Left to right.
Yeah.
Yes. So the printing happens in left to right motion on the fly, because that is how the spots get printed from that edge. So the first reference edge is your top right corner, and then it gets printed off like this. So set of 12, set of 12, set of 12, set of 12. But because the way the plate is designed, that is why the software will tell you where to put the sample. So you can decide where, how you want the array to look. So if you tell me that this is how I want my samples to look, we will feed it into, there is another option in the software where you can feed your requirements, and it will generate a plate map for you on how you want. So you can generate your plate map, you can generate your data sheet, so you can generate these looking at how you want it to fill. So if your plate right now has certain samples in certain specific locations, then the software can also go and pick up that sample from that well. So it's so flexible, because there are so many different applications. It's actually a very interesting question, and I'll spend another 2 hours telling you how we are doing this mechanism of generating the well plate. So the jet spider needs to fill up one corner of 12. Because it's in multiples of 12, it has to finish the first 12, go to the next 12 wells, go to the bottom 12 wells, go to the next bottom 12 wells. It has to finish one section before it moves printing and takes another set of 12 samples. So that way you are able to save the time it takes to move around. It'll just pick up 12 at a time, finish, go back 12 at a time, and done. So that is so when we are doing assay transfers, we show you a full demonstration of how your assay manually can move horizontally, but this is only to prepare your source plate. This is not how it will look when you print it. This is your 384 well plate. So this is something like this plate. Let me show you. This one. So this is like any plate where you put 20 microliters of sample. Okay. Now this feature of the slide shows you where you have to put your sample, so that the array can look how you want it to look. Or an ELISA can look how you want it to look. This is only for the reasons of where to put your sample. Once you know where to put your sample, you move to the next stages. This is a fun part. This I really enjoy doing because it's fun. Now, somebody give me a normal number. How many pads? Or let's take an ELISA. Let's take 96. I'm going to take it to making. So what I'm going to do is divide this full slide into 96 squares with the software. So right now, we're doing, I'll just go to, I'm showing it this because I want to show you the difference in the pitches. So let me give you a 6 by 6 example and increase the space for the purposes of explaining. I think that will be better. So with the help of a software, I'm changing how I want my assay to look. This is where the slide properties happen. The next feature when I move is the spots. So what I'm going to do now is, this is the distance from one spot to the other spot. It is called the spot pitch. The pitch is the distance from the center of one spot to the center of another spot, and that has to be consistent. If you want to give consistent data, it has to be a consistent spot. So let me decrease this. When I decrease it, what does that tell me? It tells me that now there will be some space from one spot to the other spot. And right now, because we have many samples and we have such a small area, it cannot fit all these samples. Let me go back to the basic. You said 22, so let's stick to 22. So that's my 11. And now I can so from one slide, let that be a blank slide. But from my blank slide, I have made many identical assays. Each assay contains 22 samples. So my 22 samples are distributed across the entire slide in the way I want it, because what I'm going to do after this is I'm going to post-process it. I'm going to put my secondary antibody and I'm going to make that as one reaction. And that will be my one assay done. So you can multiplex it. So right now I have given it, where did that go? Right now I have given it several squares. And I can duplicate it. So most of the work in proteomics, obviously you want to get high reproducibility, so you duplicate, you triplicate it. So the HuPro is about duplication. So you've got 19,000 times 2 features. I can triplicate, so this is how it looks. This is the final tab, how my arrays are going to look. And if I want to make them centered, I can make them centered, and I zoom in. These are my spots. And if I zoom out, you can see that each square is its own little ELISA, if that's how you want it to be. So instead of doing separately, at the end of the day, you will have a complete data sheet which will show you that my first spot, for example, my first spot, I'll increase the space because right now they are a bit clustered, so you can't appreciate it. I hope you're seeing this because it's not letting me increase it. And there is a reason, because it's reached its maximum limit. So let's see how it looks now. So this, before you start your entire experiment, you know that there is something which is not suitable, because it's either it's going outside the dimensions or it's inside the dimensions. So you can alter your entire print run based on how you want it to look. So now let me go back. I'll make this slightly smaller. And I'll make these slightly bigger. And now I will give them some space to grow. Are you seeing any difference in how it's looking? That's better, isn't it? So this is your one square. And now I have designed it, just while talking to design it in such a way that it looks pretty. It's good morphology and differentiated spots. So now you can tell that yes, this is something that I can work with, I can develop my assay. There could be many other biological samples that you can get in this square. So this is just one. So let me go out of it. That's your first row, that's your second row, that is your one slide. Like this, the same time it takes for one slide is the same time it takes for 25 slides. So really it doesn't matter if you're doing 1 slide, 5 slide, 10 slide, 25 slide. Your entire assay can be replicated identically with all these squares, which is why it gives you the fun of designing something and transferring your immunoassay or your chemical or any other biological component assay onto the inkjet platform, because many other people can use it because of the software, because it's so flexible, you can design your assay. And when I press start, I can go home. There is no need to sit with the computer, wait, which is why it's 100% automated. So finally, I'll go back to Iris, the camera which has changed the world of proteomics. Why most of the people prefer this camera is because it remembers, it recognizes, and it reprints. And these are the 3 R's that change the life of any protocol or any assay, because you don't want to waste your experiment if things don't work because of a platform that is in your lab. That's not your fault. But you don't want to then have to go back and repeat anything just because it didn't work. So we've decided to put in a secure quality system itself on the platform that it will remember. If there is anything that you've missed, if there's anything that you've forgotten, mistakes happen. It's okay. So what we are doing is we'll remember it that yes, that is the place where she's forgotten these areas, but don't worry, we'll go back, we'll print it. And that's why what comes back at the end of it as a solution is 100% yield. These are some of the case studies that I have put on the table. This is the benefits of reprinting. It's a technological advancement, and no other sort of proteomics solutions provider has a camera attached to the printer where the camera knows what sample, where, whether it's there, it's not there, whether it's missing. It will tell you a full report, and that is completely automated. So what is this camera that I'm talking about? It's called the Iris, camera Iris. It has two twin cameras on both the sides of the print head, and it flashes. When it moves from left to right, right to left, it flashes. So if you are sitting and looking at an array, you can tell that the camera is working because it's flashing. It's taking real-time images. Every time a spot is getting dropped, it takes a picture. And all these pictures get accumulated in its database in the cloud, and then it will tell you, oh, by the way, this slide has a dirt, or a sample is gone, or maybe something has been brushed off, or you're missing an antibody because you forgot to fill the well, because so many things. So it detects missing spots, artifacts, merged, misaligned, all these problems that come with microarraying as traditional microarraying are eliminated. That's how it looks. So these two are the cameras. So the camera is actually here. So when it moves, the camera flashes on the slide and it takes a printer. It takes captures an image real time of every spot that gets printed, every section of spots. So that's 12. That's 32 in a row. It will take pictures of all 12 at a time. So it's a real time imaging capabilities. It's automated defect detection. That means it's missing, artifact, merging, misalignment, all that is, it's completely quality controlled. So you don't feel that you have to go back and repeat something just because in the first time you missed something. You always have the option that you switch on the camera, it'll tell you, it'll remember, it'll go back and print it, and that's it. So look at this experiment. This is an overview slide that I created, and this is only one small square section. This is I think more than 1,000 in one square, 1,000 samples. This is just one small part of it, but this is what one of our customer observed, because he was having, it was a lab with a lot of dust particles and things like that moving, and he wanted to characterize this. So he selected his threshold, that I want my spots to have a certain threshold of quality. He chose how much percentage of missing spots he wants. So many of the high throughput proteomic research institutes have criteria. So if they want a successful assay, they have criteria. My signal should be not above, not below. My spot has to be certain percentage. I have to have certain number of assays. So you have criteria for every assay to make them successful. We can set these criteria for the camera itself. So when it starts printing, it is able to detect upon these threshold that you have set, and it will give you a positive accuracy. This is something that was developed in China. They've used the Iris for their array production in Capital Bio. It's a very big microarray provider in China, and they use our system to develop some of the high quality assays, high quality immunoassays. But the reason that the Iris works is because they need to make sure it's including all their criteria that they have in an assay, or your supervisor or the head has these criteria for making an assay work. You transfer all of those criteria onto the platform. What's a pro license? Pro license is something that has the unique ability to remember, recognize, reprint, 3 R's. And that is an advanced feature of the software that comes along with the camera. So think about it this way. You need a camera to detect your issues. But if you want the camera to remember and reprint, you need an advanced software. So your current software, which doesn't have the camera, is not going to be able to print something if it is missed without the camera. So the software that is a standard software does not include the options of a camera. If the camera is being used, it has to come with a special software that can remember and reprint your spots. That is why you have something called the Pro license. So Pro license, why is it extremely useful is it can automatically refill your spots or reprint, or it can manually do it as well. You've got advanced data recording. You can store all your content, all your data in a cloud monitoring system. So it's all up and no issues with backup and data safety, etc. So it's all there. And you have improved visual parameters. So you know exactly what is going on. And you don't need to be, so if it's a long assay, if it's going to take maybe 4 hours and you have other things to do, you can press start. You can go back, come back after 4 hours, you'll have few files waiting for you in your cloud. Right, this is my assay, this is how successful it was, how many missing features were there, whether it was able to detect all my antibodies, what is my data. It'll give you a couple of reports. So you just take those reports and then you can post-process them automatically with your secondary antibody or whichever method, RPPA, whichever method you're using to characterize. This is how the Pro looks. Now I've shown you the work that I was showing you before. If you've noticed, it was on the Pro. It showed Advanced Pro in the previous feature that I was showing you. It was ArrayJet Pro. That's the software where all the camera and reprinting happens. So it's actually a part of artificial intelligence software which evaluates your slides real time. It's automatic or manual spot refill, and it provides 100% yield, no missing data sets. So there is no need to repeat your experiments for a whole month. So it remembers that there is something that is missing here, and what it does the next time you have a spot here. So here it's blank. Remember these are the pictures that you get automatically from the camera. This is the picture that it showed without the spot. Then it recognized, remembered, reprint, and it printed the spot. So you have an antibody there. Instead of wasting 4 or 5 slides without the antibody, it is able to track, it is tracking the antibody and printing it again. So there are spot refill features. Now spot refill means you can reprint that spot. Wherever it is a missing place, it will go and put your sample. So it evaluates the likely cause of the missing sample. Sometimes what happens is air goes inside, or you've forgotten to fill a well. Because these are 384 well plates. If you fill all the wells, sometimes the human eye cannot really see if all the wells are full or not. I have had my own experience where with pipetting so many different samples in the 384 style, if you miss one well and if you put that plate to a reader, what's going to happen to that one antibody? It's not going to print. It's not going to get picked up. It's not going to get detected. So you've missed the whole set. You'll have to go back, you have to fill it again and start. So it evaluates what's the issue, whether it's an air, it's a thread, it's a fiber, it's any other problem that you've either missed it, you've forgotten it. It evaluates it and it will show you, before it starts the printing, it will show you, yes, I'm able to successfully detect it and I'm able to print it. But there are methods where you can do a manual printing as well, where it evaluates the cause of the missing sample or the empty well, where you've forgotten to put a sample in. It locates it from the whole slide deck of hundreds of slides of many arrays. It will be able to detect where exactly it has been missed. And it replaces it with the sample that is already in the print head. I showed you in the second or the first slide that it has some capacity. The print head has capacity to store your samples. So from that capacity, it will use some of the samples for this reprinting. If it doesn't have enough sample in its nozzles, in its capacity, then it will go back to your plate. It will pick up some more sample, 1.3 microliters or 2.5 microliters, and start again. And it rechecks, before it prints, it rechecks. So this is your plate map, this is what I showed you, this is your plate. Now remember, you've forgotten to fill this well, and that's okay. So what happens is, when you're doing the manual method, it'll go back to your print run, your print design, and it'll show you this is the place where your sample is missing. It'll be able to show you that this is where you've missed it. So you can take the plate, you can have a look, yes, it's missing. It's right, it's missing, I've genuinely forgotten, which is fine. Put it back, you put a buffer in, or you say, okay, it's not too late. If I missed it, I can put a sample again. So you go to your lab, quickly prepare a sample, put it back in, put the plate inside the reader, and it starts where it has left off. And then when I start this overview run, the green area is where it will show me to confirm, to double check, to verify that yes, my antibody that I just went and refilled is definitely going to get printed. It's not that I'm missing my entire experiment and the whole thing has gone to waste. It'll remember it and it'll show you just to double check. Are you happy with this? Can I start? Can I press yes? Are you happy with this? You said yes. And then, ta-da, that's it. So you've got, this is your missing. So this is your manual method where you've got the spot which is missing. You see this? And then this is your image. This is your array. This is where you've missed it. And without having to do everything again, you just go and fill this one sample and it will show you that yes, your antibodies are. So now you have complete data set. You have a complete array with all data sets to be able to characterize it. So you are not wasting enough time to go back and do it. This is the GAL file reading. This is what happens when you have the Pro license, which is able to show you where you've missed your spot or where things have gone wrong, and it has corrected it for you. And this is where your data file goes and merges on top of your sample file to give you your data set. So if you've done some work with GAL files probably before, you probably have an idea, or I can take you in detail offline with how you can do this, where it'll tell you exactly, this is my spot 0, sample set 1, this is my diameter, this is my pixel, this is my advanced diameter, this is the distance, this is the circularity 98%, which is almost 99%. So the morphology is extremely round. So you've got a nice, good protein content in that one spot. So it gives you complete details to be able to verify or plot a standard curve or get a t-paired square test, etc. So to conclude, it's multi-purpose, it's scalable, it's obviously next generation of printing, it's the fastest technology in the market, and it has a large customer base, which is why it's important to address issues in proteomics in R&D more than established industries, because here we are at a stage where we are trying to develop something and we need technology that can help us develop it faster and more accurate. If the technologies itself are not accurate, then how are you going to develop something and make it work after 2 years? So that is why we support them through grants, through any of the collaborative studies. We support R&D work because we want to develop that assay from a non-standard platform to a standardized assay which will work. And we have got an experienced team. So totally, I think from all of us in the team, we have about 75 years worth of microarraying, RPPA, NAPA, HuPro experience, which is why we are able to support all these industries that are here today who talk about printing. Arrays are printed. What did you use to print them? So if they are having any issues with printing arrays, then we are not only promising improved results, but we are also partnering, and it's a joint effort to make sure that the assay is a little more sensitive, highly sensitive than what you were previously getting, but it's also highly accurate. So you're saving a lot of time. If you've got any assay that you want to discuss with myself or my team that you feel we can totally transfer and it'll save me time, money, and energy, let me know and I'll be more than happy to talk. Thanks.
I am sure by now you are convinced that while it seems it is very easy to do microarray based experiments and one could screen thousands of proteins just with the small volume of the patient sample or clinical sample or even small drug what is available to you. You can just have few microliters of droplets and put on the microarray slides and get data for thousands of proteins. However, to get reproducible data and meaningful data which could make sense is not so easy, and that is where lot of technical expertise is required. I hope you are now convinced that microarray printing plays a really important role, and technologies like bioprinting provides innovative solutions to the researchers for the biomarker discovery based programs or drug development programs or to even various diagnostic based companies. So, microarray technologies, microarray printing platforms, especially from the ArrayJet which we discussed today, provides unique non-contact inkjet printing to offer throughput precision and consistency, and it could deliver high quality reproducible microarray based printing, which is I think really required if the goal was to perform experiments on large number of samples. If you are doing experiment where you need only 3 slides, probably even with very minimal variability among the slides, you can still do corrections. But when you have large number of samples and large number of microarray slides to perform, then a technology which can deliver high reproducibility with a high throughput manner, that becomes very, very crucial. In the coming lectures, you will be exposed to more such advanced technologies and their applications in high throughput areas for various type of life science applications, including clinical applications. Thank you.